So just a bit to make the connection of anticipation and the robotics. So I show you this kind of example, but this is even like an old video, but you see like the robot wants to actually give a drink to the kind of person, but it doesn't really anticipate that the person is moving away the cup. So just playing the video again. This is just like an illustration. Come back. But this is just an illustration which actually shows that if you talk about human-robot interaction, so the robots need to anticipate the behavior of the humans to actually do the right planning. And but in computer vision, there has been a large focus to analyze what's going on. It's like we have large data sets nowadays, image data set, a video data set. But in terms of the anticipation part, there are actually different tasks. And I wanted just to mention a few of them. And that's just like pick one of the tasks and give you some basic what you can do and how you can address this kind of task. So the first task what people actually do, this is actually called early activity recognition. So in this kind of the setting, you have already, instead of observing the action until it's actually completed, you try to predict what's going on before the current action is completed. So this is called early activity, which means like the action has already started, but it has not been completed. So this is highly relevant when you want to recognize the action before it is completed. But this is actually a relative simple task because there is actually one thing that can happen, right? Because you know already how it started and you know there's only one label for it. If you go to before kind of anticipation more for longer time horizons, then technically, give an example, you know it's from Bonn train station, probably also Dortmund. You run down, you're trying to catch your train, but at the end, if your train is on time, you might actually miss it. But with the Deutsche Bahn, in most cases, you still manage to get this right train. But it also shows that there are different kind of opportunities which you can happen in the future depending on certain kind of factors, and you don't have not all the information. So you also need to a little bit understand how you deal with some kind of uncertainty in the future. Other kind of task, which is a bit illustrated here, is like if you want to anticipate where the person's going. So given different examples. So for instance, like a person standing here, and you actually try to predict this kind of the heat back in which kind of direction the person is actually moving. Also here, another kind of example, the person's here, the car. In most cases, people take the official path where the car enters, but some people also seem to move for the other direction. So in all the cases, you have some kind of probabilistic representation where the person will actually move. So it's also there where the person will actually cross the street. So other kind of task is also like forecasting of human motion, which means like you have the pose given, like this is the ground truth, and you actually here just like for 1 second, you actually try to predict and forecast what is the next full body motion. And here's kind of different kind of older models that actually try to predict. So in this lecture, I will only focus on actions, and I will give first like a very simple approach, which actually gives you an idea how you can implement it. Which is kind of the setting is like we what I mentioned before. So the person is doing something, we have a video given, and then we want to predict what's happened next. This relative short time, just what happened in 1 second. The forecast here is not directly on the semantic level. Instead, what is actually done here, you extract features. You take whatever your video data, you have your network with extracted features for each of the frames. And now you want to actually predict, so given my current information so far, my last frames, you want to predict what is the feature, the visual representation of the video content in 1 second. So the network to do it, so you have any kind of a feature extractor, or you can take a ResNet, you can also take Dino features, whatever features you want to use, it's just like a representation. And the network to make this kind of prediction is actually in this work relatively simple. It's also a bit shown here. So we have the gray or some of the frames is my past. And now in 1 second, I pick a frame, I extract my whatever features here, whatever network you take. And now you want to predict the features in 1 second in the future in your video. The setup here is straightforward. So we have a convolution network, so the kind of fully connected layers. But there's something which is relatively interesting here because it doesn't have a single head, but it actually has k heads. And this actually is a little bit related, if I jump a little bit back for 2 slides, is and we might have different futures. We have not like a single one, but there might be different futures happening, and the model is not predicting a single feature representation, but actually k feature representation for compensating for k different potential futures. And the thing is like how to then train the network. I mean, you need to actually solve two things. First, you split the heads to have like instead of one prediction, directly k different prediction or k potential different future scenarios. And when you train the model, you now need to be a little kind of careful because you don't know which of the potential future scenarios you actually have there, right? So you have a network which predicts the feature in 1 second, and now you want to train it. And now you have to say, well, you can average the heads, but that would be not very smart, right? Because you want that one of the heads predicts the right future, and the other thing, the other k minus 1 heads might be also reasonable, but they exactly not which is actually observing here, because we observe only one future, but multiple futures could be possible. The way how they train it is actually rather straightforward. The first thing what you're doing is to figure out what is kind of the right potential futures. You have your network, this is your parameters of the network. And now what you're doing is like for each of the k heads, so we have k different heads where we predict k different feature representations. And we simply like, look, which of my head is closest to my feature presentation, what I have in my observation. That's my ground truth. And this technique means like, I not simply average the count of the heads, but I make a prediction. I check which of my heads in my network is actually closest to the ground truth. This gives me now the indicated set. And now when I actually update the parameters of my network with backpropagation, here I simply take the parameters of the head which are closest to my ground truth. So it means like I just like update the parameters along a single head. Yeah.
But wouldn't that possibly result in problems if during early stages of training, one of the heads is close to the image we had before, assuming that there's some kind of video that doesn't change all too much over time, and the others predict some absolute nonsense.
Yes.
And you might just have one head that is constantly shifting between different features.
In theory, that could happen. It could also happen that there's only, in all the cases, there's only one head which predicts, and the other heads do just like random noise, and they're never matched. Theoretically, that could happen, but at the end, in practice, because you have this variation in the part, it actually also learns that actually uses all these kind of heads. So because if you have enough variation in training data, it turns out that this is actually not an issue. If you would have an issue that we also did in some other works, you can also add a regularizar, which also enforces that at least some of the heads are a bit selected. So you could also address it if you observe in the data. In their work, they did not have any issues. That technically not always the same heads are selected in the same amount of time. But at the end, just when you train this counterpart, it was actually they didn't observe major issues. But you're absolutely a bit right. I think it also depends a little bit, if we go a little back, how many layers you technically a little bit have. If you have even like starting from the beginning, then it's more likely that you would actually have this kind of observation that some of the branches in the network is not used at all and not trained at all. But they did not observe this kind of issues because depending what is like the features for selecting, it always picks something. And this is also what we also observe if we have other so-called mixture of expert models. There is usually never the case that one of the experts is never used. It's more the case you have a high imbalance that maybe one head is used in 90% of cases and the other head's only in 10% of the cases. That actually can happen. Huh? So, and now you train these kind of parameters through the corresponding head, which fits best to the current ground truth, and then the rest, the backbone parameters, are trained in all the cases. So that means when we now have inference, it predicts k features all the time. And then the features is usually not what you're directly interested in, but then technically take the features, then they have some kind of a simple action classifier on it. But they could also have like object classifier, whatever you're interested in. It's just like a generic feature representation. What they do in their work, which might be not always the best one, the simple take for the final prediction, just like the average. Although that's not usually the best case, but it shows that the prediction on the next slide what they actually get. So they train it with like 3 different heads. So you have, this is the showing one frame, but you have a sequence of frames. This is like your input observation, and it's a very simple task. You have only like 4 classes: handshake, high five, hugging, and kissing. So this is the 4 action that can happen. And here you see the prediction of your 3 different heads for the same input. So you see that technically the first 2 heads, they actually prefer the yellow class. Assume in 1 second the 2 person might kiss each other. And the blue one is like still kind of probably for hugging, but the third network here has a strong preference that the hugging will be the next action. If we then average over this probability over the 3 branches, then here the prediction is like the highest probability is for kissing. So this is also you can think about like an ensemble, what to do for the prediction. Another example, that's my input frame that I observe. And then the network here, the 2 networks, you see here in these 2 cases, they look that it's always predict the same. But we see in the third example, the 2 networks make very different predictions. So depending on the inputs, so sometimes 2 heads are very similar, but for a different input, then they completely change the prediction. And this also, here's another example where also 2 networks very confident of the red action, and the last network here more favoring the hugging, and the last network also here also a difference. 1 head prefers the green action, which is high five, and the other 2 networks prefer the hugging action. And this is kind of the averaging over. So now let's do play a short a test. So people in Dortmund, you're also welcome to give your answer. Just shout in what you actually think will happen next. So the first example, what we have already seen, that's like my observation. So just like a very short clip. Now the task is what will happen next. So this example was already on the previous slide. You can never think about it. Again, we have only this 4 different actions: handshake, high five, hug, and kiss. And now it's like, what will happen in the next frame? It was already on the previous frame, but what would you guess?
First one, kiss.
Kiss, exactly. That was already on the previous slide. So this is actually also predicted by the network, and this is also observed. So now let's start with some new examples. So what do you expect will happen next out of these 4 actions? High five. Any guesses from Dortmund? Feel free to just say that.
High five. Hug.
Okay. Let's have a look. And high five is exactly what is happening. So just like disappeared.
Yeah.
Okay. Okay, appearing again. Okay, so let's continue. So now we have the last example here. What do you expect? What will happen?
Hug.
Hug. Yeah, looks like a hug, and actually hug is actually happening. So I just have like 2 examples, which one has some ambiguity. What will happen now? Just the top row. What do you expect?
Handshake.
Handshake? High five?
Well, it could easily be something in between.
Yeah, it could be also between, but here we are constrained. I have only 4 options. I mean, it's clear one wants to give a handshake, the other one wants to give a high five. I think if one knows the TV show, one probably knows what will happen. So it's a high five in this kind of the case. Just, but it also shows the reason why you want to have this multiple prediction, because at the end here we show just like the action with the highest probability, but at the end there is some kind of ambiguity, right, in this kind of the case. So now we come to the last example. So what do we expect what will happen here? Again, only the 4 classes: handshake, high five, hugging, and kissing. Also from Dortmund, just shout.
Kissing.
Kissing. Kissing.
I mean, again, it's very not even necessarily defined that we would be capable of ending up in only one of the situations. I mean, you can kiss while hugging, you know, and it looks like we're about to do both.
That's true, but at the end, if kissing and hugging, then will be labeled like kissing.
Okay, then I would say kiss.
Okay, let's have a look. So you are very relative confident what will happen. It's a high five, but it's another person which were not in the observation shows up. So you have sometimes out of context And this actually can easily screw up whatever you predict. But it's just like to summarize technically, when you do this anticipation part, you have to be a little bit careful. You need to handle the uncertainty part. And this is showing a little bit kind of different ways how to do the forecasting and how to handle this future uncertainty. So this was a very simple approach. So this is also something what you could easily implement. It's not very complicated, but it has obviously very disadvantage. So it only predicts for either 1 or 5 seconds. So you always train for a different horizon, and it just predicts what is happening in a fixed horizon. There's not like a longer horizon for the prediction. It also predicts just the features, which is usually better to directly predict what you want to have, like what is the next action, for instance. And what I also mentioned, it's relatively inflexible. Yeah.
I would also say a major drawback of this is that it doesn't take the history into account. It only takes into account a singular frame, where we would not have information about things such as velocity. If someone is quickly approaching someone else to hug them, that would, for example, could be important for the prediction, but we do not get this information by just looking at a single frame.
Yeah, absolutely. And this is technically straightforward, but adding like multiple frames is also straightforward. But now what I want to talk, the rest of this kind of lecture is like, now we have multiple frames as an input. And we not only want to predict an action at 1 second, but we have a long time horizon of like seconds or minutes, and we want to exactly predict what action will happen and how long they take. So it's like much more information than just what is happening 1 second. Is let's say, okay, what will happen in the next 2 minutes? All the actions and how long they actually will take. And this is actually very helpful if you think about human-robot collaboration. So at the end, if let's say the person needs some tools, and then the robot knows, well, okay, maybe in 2.5 minutes, the person will start preparing something, and I can also provide the tools what the person actually will need. So this is the application context. So just like to summarize the task that we have, that's my input. I get a video, and now the rest, I'm just showing the videos happening, but that's not any given to the algorithm anymore. Now what you want to do is like you want to predict what is actually happening in the future, and this white bar is just like going over the frames of the future frames. So this is now our task. And I will now describe different models and architectures, how we can actually achieve this. So starting with a very simple one, and then later looking at more advanced algorithms. So the first thing what we can do is like we take a relatively simple approach. We first take our frames. And what we do first is like we try to understand what's going on, which means like we do for each of the frames, we estimate what kind of action is going on. So this is like later on, we go directly end to end from the feature to the forecast. But here we have first an immediate step. We actually convert my observed video sequence in a segment of actions. This is the observed part. And now from this kind of the information, that's my action, what I have observed in the past, what will be the future actions. So given this observed part, what I actually do is like here, there's the task. I want to predict what are the future actions. And this is like one approach is like we take a simple recurrent neural network, which means like first we need to discuss how we encode the observation part. And what we do here is at the segment level for very good reason, because technically you might have one action which goes for a long time, but then you don't have the context what kind of action happened before. So if you have everything encoded per frame, that means like you have a lot of repetition counterpart, but you have like not very compact representation. So in this case, it's like for each action, we just like store what was the duration of the action, and then one hot encoder, what was the reaction label. And these different colors here are simply 3 different action labels. And this is also you see here, so this action has not yet completed, so we also need to understand how long my current action needs to be completed and what will be the follow-up actions. So taking this as an input, we simply use recurrent neural network, and this recurrent neural network makes 3 predictions. What is the remaining length of the observed action? So this is exactly what I've shown here, because the last observed action might continue for some time. That's the first part. The second is like what will be the next action, so the label of this segment, and how long this kind of action will be. So the 3 parameters that what the network predicts. And they have like longer horizons. We take this as a prediction. And now the first thing what we do is like we take, that's my previous action, what I've seen before. And then technically what I do is like, because I now predicted how long will my current action need to end. So I update the length based on the prediction here, the remaining length of the observed action, and here the future action label and the length. That's the two output here. I also concatenate them. So it's some kind of autoregressive way where I can continue and so on. Again, feed it in my recurrent neural network, make the same prediction and so on. So this is the way how I can actually make also long predictions. The way to train is actually rather simple. It's just like exactly what we predict. The future action is just like the cross entropy part. We just take a mean square error loss for the remaining lengths. Head is always the ground truth. This is like with the prediction, and that's the duration of the next action sequence. So it's straightforward to train and to model. There's also another simple variant. You can say it's like, okay, you take a different encoding. You could also do it more as a frame level encoding, or what you can also do is like you subsample your observed frames. So you might not take every frame, but every second frame. And this is like gives you then the duration counterpart. So this S is actually the duration for the sample from the observed part, and Z is just like the classes again, what code encoding. So each row corresponds to a class, one vector encoding, so everything is 0 except for the class which is present, and this here is just like the sample point. So we have the gray action, then sample frames from the cyan action, and then sample frames from the green action. Again, now you have a convolution network which also does a prediction, and this is then converted back into this format to also make a prediction. So let's first have a look at some of the results, what you get. So far, this is the observation. So we see also observation is not perfectly recognized, but now as soon as I cross it, the black line. So then I'll probably start again.
They can still see it in Dortmund. It's just a problem with the beamer here.
Yeah. It might not like the videos. Okay. So I'm playing again. So technically, this is about the observation, and as soon as it crosses the sharp black line, then the video I see is not anymore taken. So now starting with the forecast. And this kind of forecasting technique, what I see is like from the blue one, which is technically there. Sometimes it's correct, but there's also some kind of the mistakes. So let me see to jump to another video. If it maybe shows up again.
Do is okay. So also I just sent the link to Zoom over the eCampus mail, so you can log into Zoom and everybody in Dortmund can see the slides. You can see the slides.
I see all the slides, yes.
You can feel my shoulder if you don't.
But also that shows that in general, if I don't see it directly here now on the screen, it's like the RNN is usually like giving slightly better estimates. It's better aligned with the ground truth. And this is just like the last example, so it's kind of different. You have a top view, camera view, and there people prepare different types of salad. So at the end, here's also like different kind of, not really such a fixed order because it doesn't really matter when you add some kind of ingredients. And also what we see is here, so far as the observation, now my bar is actually crossing the black line. And now it's technically we have the prediction. So again, we would have at the bottom seeing the ground truth, and also like the RNN does kind of a reasonable prediction to what's actually a bit predicted. Yeah.
But isn't there the problem that we are predicting the actions, and I suppose in whatever way you predict them, we will get probabilities for the different actions and not a one-hot encoding.
Yeah.
I suppose we get to one-hot encoding by just taking the maximum.
Yeah.
But doesn't that lose some information about action ambiguity? So if for some reason in the observation we were we might want to take into account the information what the adjacent actions were, for example. So if for a long period of time we have an action that we out of context know that it really takes a long time, but then for a single observation we have just like 0.55 probability for the wrong action and 0.45 for the correct one, and then we're at the correct one again.
Yeah.
We might want to avoid considering that to be the wrong action when we could have seen, okay, this is surrounded by things that are the other action, and the other action is also somewhat likely, so we want to denoise it to some extent.
No, I absolutely agree. So we start with simple approach and then we address things, making things better and better, right? So the thing is like, so at the moment you're right. So the approach has two limitations. First, you predict the action of the observation. You just take the max probability. So you lose the information of the ambiguity in the observation. And the second point, you just make like a single prediction for the future. Both of the things are not optimal. And I will also now show like how things can be done better, right? So step by step, we make the approach a little bit more complicated and better. Yeah. So at the end, it's like, so to see just like what is the difference if you want to measure quantitative between the RNN and the CNN approach. So we see like this is like the amount what you predict in the future, and this is a measurement for higher numbers are better. And you see technically from the blue line, which is the RNN, so you have different amount, how long observation you feed it in. And you see in most cases the RNN is doing better than the CNN, but in some cases the CNN is also doing better. But this is the results where the observation is not really estimated, it's using the ground truth labels. And if you actually feed in the estimation where we also have errors in the interpretation of the observation, we see also that the numbers here, it's getting lower. And there's also sometimes a kind of a mixture regarding the better results. But nevertheless, if you compare to the first approach, you also see kind of the first approach where you first predict features and then you try to predict the actions. So this is kind of a setting we also only predict for 1 second, because the first approach, what I mentioned, it only works for a single interval. You also see that if you have a better model, you directly predict the action, you also get much better results. So now this is just like a very simple baseline. And now we actually talk about how we can actually improve the model. So the first thing, what we can a little bit consider is some kind of consistency between the past observation and the future. So we stick to our RNN approach, or whatever we have now the frames. We don't do first the segmentation of the observation part and then a second step. So now we directly make the prediction directly from the features. We still have the RNN approach. Again, also here we have a simple like start of sequence and end of sequence. And now also this RNN predicts in a slightly different form, but still for each of the segment, what would be the action, what is the duration, what would be the next action, the duration, what would be the next action, the duration, and so on. Since we have a fixed length, we don't know how many actions will happen, therefore the network predicts the end of sequence. So that's the same what the language model would actually do. To have some kind of consistency, you can also say it's like, well, when you predict the future, you should be also reverse the time and also be able to predict what happened in the past. So you can actually improve the training of the model to actually ensure that the features which actually have passed through to the end of the RNN, that it still has the information of the observation. Because there's always the risk that after the first action, it throws away some important information which may become later relevant. But what you do is like you feed it back. Again, you have the sequence, and you also try after the forecasting, also try to a little bit understand, okay, what exactly were the actions that actually have been happening in the observation. So this is just like enforcing the network to not to be too selective on the information which is actually there, but still keep the memory information what actually happened in the past. And the other thing what we also can do to change is instead of just feeding into a simple RNN, we take the features, we have some kind of a convolution network before. Also here, additional loss, so we make sure that the features what we learned, they actually learn semantic information. So we have the loss here, ensuring that my TCN, I will describe it on the next slide, that this actually tries to understand my occurring actions as good as possible. I have my loss for the future actions, and I also have like the same loss on the same observed ground truth. But this is then after the forecasting, again, try to reconstruct what have been my original features. And just like this TCN module, which is like here, this is just like straightforward delayed temporal convolution, which actually means that for each of the layer, so the dilation factor is getting larger. So we have like, you take like every second frame, every fourth frame, every eighth frame, always to the power 2 to the power of I, where I is the index of the corresponding layer. And this is technically what we're also doing here. So you see in, so get some kind of the frames, when you feed it as an input, you feed it in this kind of the network with temporal convolution layers. So this is like a combination of window, one-to-one, and a skip connection. And then for each of the frame, you predict what is the probability of the action layer. And you can have like a single stage, or you can have multiple stages. And the multiple stages, technically, you have a loss after each of the stages, and this actually gives you better results. And there's actually very different kind of flavors. What you can also do, you can also like, okay, not again. And you can also combine different kind of dilation factors in parallel. Huh?
Everybody has the.
Okay.
Everybody can see the slides, so still on.
Okay.
Their computer.
Anyone can say where is Zuniga? I could not find it on eCampus.
Oh, I sent an email to you, so it should come in your email inbox. Did you find it? Oh.
Just that I was not registered on campus specifically, so
I'll give it. Overheated, but I don't know, we'll see.
I'm not sure.
Yeah.
So again, so we still have some kind of beam issues. That's the reason for the people who don't know why sometimes I make a short break. So let's see, until we are back to the network architecture, maybe jump to the next slide. Okay, so this is more or less kind of the architecture. So we have the frames, and now we also have this kind of prediction module. And now we do not have the two-step approach where we first do the segmentation, but technically even we have here the loss to enforce that this representation try to learn the semantic information of the past. Everything is now trained to end. And to end, that means like any uncertainty is part of the features that you pass through. So we don't make the hard decision anymore what action actually happened in the past. So we provide more information, including also motion information now. So, I mean, numbers are actually not that interesting, but you see that the difference is like, that has been the models before. And this is like, when you feed these kinds of features, you get actually much better results. And this is for all kind of the settings. But this was kind of the part, now you do the prediction, directly take the video frames as an input, and you try to predict what's happening in the future. But what has also a little bit mentioned before is the future also has some uncertainty. And this is a little bit what we see a little bit here. So this is your observation. And now that's like what the person is doing. So there's not all action annotated in the data set, but he has taken a cup. So we see it like it holds a cup in the hand. And from this information, that's the only what they have. And again, now you need to predict what will happen in the future. And this is now the question. So given the kind of video, now I give you three options, A, B, and C. So in the first case, the person is doing something like making coffee. So it's like pour coffee and pour milk. The option B, the person will add some feedback and preparing tea. And this food powder class in this data set, that's actually more related to making like hot chocolate. So now my question is for you and the people in Dortmund, what do you expect will happen? A, B, or C? I will show you the video again, and I can think about it, and then let me know what you think will happen. So this is the only observation was given by the network. The person takes a cup. And now comes the question, what will happen next? A, making coffee. B, preparing tea. Or C, I'm preparing hot chocolate. So what do you think? A. A. C. ACC.
I must say I do not know. I did not recognize in the video where, for example, a coffee machine or something would be, because we did see like a hint of motion of the person after picking up the cup. So if we knew where the respective locations are, where I would have to go for each of the three scenarios, then we could perhaps from that motion already deduce which they are. But sadly, I do neither see like the coffee nor the tea nor something. I do see the milk, but for the coffee, you have to go to the coffee person and the milk. That's the scenario A you're given. So I don't know.
Okay, so we have 2C, 1A, and
I have just saw like a teapot on the foreground.
Teapot.
So my answer is B. Like
okay, so someone has seen some kind of the hit. But even there's actually all the things a bit there. It's, I mean, the color is kind of dark, but at the end here, there's some kind of tea. And actually, indeed, a person is actually preparing tea. But your mark was right, depending. So even if there's some tea on the person might still take a coffee, right? And the thing is like, this person is not part of the training data. It's not like a personalized model. It's just like trained on a set of subjects and they actually try to predict. And that's the network should also do, right? If you have the ambiguity, then it should not make a single prediction, but it should have multiple prediction. And this is exactly shown here. So this is exactly what happened in the video, but now you don't generate a single sample, but you generate multiple samples, which actually represent potential future what can happen. So this is a way how we can model uncertainty. Instead of make a single prediction, you actually make multiple predictions. So going back to our very simple model, how we can simply modify it to just like making multiple predictions instead of one prediction. And this is actually very straightforward. So again, this is going a little bit back to the model where we have some kind of observed part. So first we extract here the labels or what we estimate of actions at each of the frames. And now what we do is like we don't predict the 3 heads, but what we predict is first given the information. So this is just like the information what I had here. So what are the different actions and how long they're, the length of the actions. What is the probability of the next action happening? And since I predict my network OS probability, now I can sample from this distribution an action class. So if it has like a high probability for certain actions, it's more likely that it will be sampled, but also other actions can be sampled. That means that each forward pass, due to sampling, I might actually sample different actions. And the same is like if I have an action sampled from this distribution, again, I predict the probability of the length of the action. So now it's also conditioned on my sampled action. And again, I sample a length value from this distribution, which means like in each forward pass, I have now a sampling process involved. That means like for each forward pass, I can sample different action and different lengths. And this you also see is like you see the variation of the different kind of the lengths of the actions. And also you see different color, also different kind of the actions. So this is a very simple way how you can actually modify it to make this kind of happen. So now for the rest part, we will actually talk a little bit more sophisticated or more interesting approaches of modeling this uncertainty. And what you also a little bit mentioned is like, okay, not showing again on the screen. But we had on one hand the uncertainty in the future, and what you also mentioned is uncertainty in the observation. So before we said like, well, we feed in discover the features as they are, which already gives some information about motion and also uncertainty. But we could also like, instead of saying just like that the observation, just like predicting as like a single label, we can also try to model the uncertainty of the observation directly. And this is actually what we do in the next part. If it's actually showing, yeah, so every third slide is working. And also taking there, so you have now modeling of the uncertainty if I bad light conditions. So for instance, it's also not sure if zeros are added or if a t are predicted, but the uncertainty in my observation always has an impact on the uncertainty in the future. And for this kind of the model, we use a so-called diffusion process, which actually means like diffusion just in a nutshell. If you take a data, you add Gaussian noise, everything is from the noise, but the interesting part is the reverse process, getting from noise, you want to reconstruct your data. And the backward step, that's more or less the interesting part. And for the backward step, it's like you have a network which actually tries to step by step, slowly denoise the signal. So in our setup for the forecasting task, how we use this diffusion model for exactly the task described before, we take our observed video frames, and we also take the future video frames, we just do zero padding. So we simply set everything to 0. And we add this kind of the Gaussian noise, so it's kind of a conditional diffusion model. And then from this kind of the Gaussian noise, we sample from it, and then the network actually generates for each sampled noise a different prediction of my past actions from our observation and the future actions. So this is like what the network is doing. So if you zoom a little bit in this network, so just like zooming in a little bit in this kind of this blue box part, the network structure is done in the following way. As I mentioned before, my input are my past frames. I do zero padding for the future frames. I add my Gaussian noise, and this kind of the blocks are now repeated. They just like denoise is kind of the signal until we get like a sequence of actions for the past observation and the future. And yeah, and there's one aspect which is actually here in the blue box is so-called this gated convolutions. So the network can actually activate and deactivate features. So gated convolution means like we have here sigma function, which has sigma values between 0 and 1. If I multiply my feature with a value of 0, I deactivate this feature. And it's now a little bit interesting to see what kind of features are selected. This is just like the visualization of the gating function. So this is at the early stage of the network. This is the observed frames, and this is like the future frames. And you see that at the beginning, the network just picks some kind of the features. So this is like features of the observation. So like 64 channels in this case. So the yellow part means like features where they have a high gating value. And at the beginning here for the future, it's just like smooth gradients. So it's not very selective. Some channels are a little more important, but there's not really a hard decision which information to take. And because it's in the beginning, we start with zero padding, we add this information step by step. In later layers, you see also that some kind of channels become important. And some of things, they just focus a bit on the observation. And some, they also transport the information more in the future. So this kind of the channels, this is also a way how to select the information party when you have very long time horizon. So you can actually select which information is actually relevant. So this is already the last video I wanted to show. This is exactly kind of example. Now you have also showing like both the predictions and you had also sometimes from the observation. So every time when stack line becomes red, then you switch from observation to the forecasting part. So just like another example, so here's like a confusing because red is cutting the orange, what you see on the top. And this gray, this part is like cutting fruit. I mean, fruit is an orange, but in this data set, the orange has a specific label, which also causes some kind of confusion. And again, it's like when it becomes red. Now it starts the anticipation, but you see it like it got confused regarding the classes, also like the future actions are a little bit switched. So this brings me to the end. Just kind of an overview. Some of you I know from my lectures, some of you I have not seen before. And the thing is like, so if you're a little bit interested in the topic, so at the end we always offer, usually for the first semester, the computer vision lecture. Then we offer the lab in the seminar each semester, summer and winter semester, and the advanced computer vision lecture, which is more the machine learning for computer vision, is always offered in summer semester. And if you have taken some of this kind of the modules, you're always welcome to ask for a topic for the master thesis. I think this brings me directly to the end of the first session. And we will then soon continue with the second session with Grade given done by Sven Beke. But maybe are there some questions? So I'm not sure how much time pressure we
take
have.
a couple of minutes for questions because
Okay.
there are delays for
Any questions? Or any questions from Dortmund?
No questions from here.
No problem, because at the end I already have filled the time of my slot and we can then actually continue on time with the next speaker. So thank you everyone for your attention.
Thank you very much.